The Manhattan Project, which began in August 1942, created the atomic bombs that helped bring about the end of World War II. This video is a dramatization of the development of the bombs, focusing on the individuals who devised them, especially Dr. Robert Oppenheimer and General Leslie Groves, as well as the key worldwide events that led to the decision to create and use the bombs. Many visual images are employed to portray the principal people and the equipment needed to make the bombs. The presenter is Professor Richard Leo, who taught physics at Grove City College for 37 years and was named Professor of the Year in 2004. In addition, he served as a captain in the U.S. Army and helped develop the first around-the-world satellite communication system. His background in physics and the military make him uniquely qualified to present this engaging story of how the atomic bomb was created. This presentation was given in 2020 to commemorate the 75th anniversary of the bombing of Hiroshima on August 6, 1945.
My name's Robert Oppenheimer. I was born in 2004. That's 1904, in Brooklyn. I'm an American Jew. I lived in Brooklyn area all through my early years, but I was always kind of weak and frail. My dad sent me out to Los Alamos, New Mexico, to a boys' ranch for a time in which I could ride horses and get some strength back and get my health back. For those of you who are familiar with the Manhattan Project, the name Los Alamos should already ring a bell, as it will appear later in tonight's presentation. When I was 18, I entered Harvard. I wanted to major in chemistry. My typical course load was 6 courses for credit and 4 for audit. I loved the sciences the most, of course, but I also loved French literature and the languages. I graduated in 3 years and wanted to go across the ocean to England. I wanted to go to Cavendish Labs at Cambridge, the world's most famous labs. The Cavendish Labs had been headquartered by Ernest J. Rutherford at the time that I went there, Nobel Prize winner for discovering the nucleus. I wanted to work for him, but he said my letters of recommendation from Harvard were not good enough. So I decided to work for J.J. Thomson, who had been head of the Cavendish Labs before Rutherford had been. J.J. Thomson had discovered the electron, and Nobel Prize winner for that reason. I worked with him for about a half year, but I realized that experimental work is not my cup of tea. So I thought I should go to a place that more is emphasized in theory, where to go but the University of Göttingen in Germany and study under the great Max Born, a name that most of you have never heard of, but all physicists adore him. Nobel Prize winner, yes, for those of you who have quantum mechanics. If you remember, psi squared is related to probability. That was his idea. But what he was most famous for was developing the minds of young physicists, or even older physicists. Physicists loved to flock to him to learn. He had that ability to draw out the best from the people who worked for him. Nobel Prizes winners, here's 3 of them, all wanted to study under Max Born. I was there for 3 years, and when I finished, I had to do what all PhD graduates had to do at Göttingen. You jump into the pool, you wade across the pool, you climb up on the goose girl and you give her a kiss, and I did it, yeah. But I was told that I should increase my analytical ability. So where to do that? I went to Wolfgang Pauli in Zurich, Switzerland. He was a theorist. He was not an experimentalist. Physics is in the two categories, and boy, this guy is not an experimentalist. He had a reputation that anytime he walked in a lab, things broke. In fact, his recommendation was such that if he passed through town, the things in that lab broke, even though the people in the lab didn't know that he was in town. And that's documented. I don't think he knew the difference between a pliers and a screwdriver. But a mind, let me give you an example. When he was a freshman at the University of Munich, Herr Einstein came to give a talk to the faculty. And after Einstein gave his talk, he sat down and the chairman of the department said, does anyone have any questions? He's addressing the physics faculty, of course, because those are the only people allowed to ask questions. But nobody wanted to ask a question of Einstein. He was at the height of his popularity at the time. But the fellow in the beanie in the back row, he had his hand up. I'm sorry, only faculty are allowed to ask questions. But no one else. Einstein said, well, let him ask his question. Well, what's your question? Pauli walks down the aisle, picks up a piece of chalk, writes in the blackboard, puts the chalk down and says, and that's why I think Herr Einstein is wrong. Age 18. Einstein gave it some consideration, said, I think he has some possibilities about that. I'll have to think about that some more. Pauli helped me increase my analytical abilities considerably. After being there for about a half a year, I came back to the United States. I turned down an offer from Harvard to take two offers out in California. One at the University of California in Berkeley, the other at Caltech in Pasadena. Yes, I know, 400 miles apart, but I would spend a semester at each one, alternating. But most of my work was done at Berkeley. And shortly after I got there, the events of the world started to impact us. Adolf Hitler came into power in 1933. He was an Austrian, actually, but had taken over in Germany. And anti-Semitic discrimination started occurring. And this is what some of those rules were. They caused 100 physicists to flee to the United States because they were Jewish. And look what it did to some of the universities. And this flight of the eggheads to the United States is one of the prime reasons that the United States became the leader in the world in sciences. This huge influx of German Jewish people or those sympathetic. And about the same time, the great Italian physicist Enrico Fermi was working in Rome. Unfortunately, Italy did not have very good physics backgrounds, and the money that he had to spend was very, very limited. Nothing like at Göttingen or Cambridge. But he was bombarding neutrons in 1934. They were just discovered in 1933 by Chadwick back at Cavendish Labs in Cambridge. So everyone was kind of bombarding with the could with neutrons. He discovered something called slow neutrons. Now, what's a slow neutron? That implies there's fast neutrons, and yes, there are. And we distinguish between the two of them. A slow neutron travels at about 200 meters a second. That's 2 football fields every second. That's slow. I know, for you that's fast. A fast neutron travels at about 2 million meters per second. So there's a big, big difference between a fast neutron and a slow neutron. And in the world of nuclear physics, there's a big difference between fast and slow neutrons. We'll get to that. He was bombarding things with slow neutrons to see what would happen. He's a very organized man, so he thought he'd do the whole periodic table, start with the lowest sized elements, and build up until he finally got to the biggest one, the last one, 92, uranium. Too bad he didn't start in the other direction. It would have saved himself a lot of time. Because when he did uranium, he noticed something unusual happening. He wasn't sure what. And again, because of the limits of his money, he was not able to pursue this too much. But he knew something was going on, and of course you publish this, and other people are aware too, that something unusual was happening when you bombard uranium with neutrons. A few years later, in 1938, November 10th, Fermi learned two things. First, the night before, November 9th of 38, was Kristallnacht. That's the German word. In English, crystal night. It's the night in which crystal was broken, glass windows. It's the night glass windows were broken throughout Germany through the Jewish establishments. Hundreds and thousands of Jewish establishments had their windows broken and people taken away and put into concentration camps. All in Kristallnacht. And why is that important? Enrico Fermi's wife, Laura, was Jewish. And now that meant that there were real problems for her and for his family. Later that evening, he got a phone call. It was from Stockholm. And they informed him he had just won the Nobel Prize. Two pieces of information he learned in the same night. And about the same time, two people in Berlin were doing research. Arohan and Lisa Meitner. Arohan was a native German. He was an Aryan. He was not Jewish. Lisa Meitner was a physicist. Otto was a chemist. Lisa was a physicist from Austria. She was Jewish. It is uncertain if Otto knew that she was Jewish because very few people knew it. She was okay in Germany, even though a Jew, because she was an Austrian, not a German. But you're aware of what happened on September 1st of 1939, aren't you? Well, before that, Germany took over Austria. And in taking over Austria, Hitler said, all Austrians are now Germans. That meant that she is now a German. That meant that she follows under the anti-Semitic discrimination. That means that she is going to have problems if she stays in Germany. They had been bombarding uranium with neutrons, and they had noticed some strange things in the sense that because he's a chemist, he could analyze the material after the bombardment of uranium. And they would find things like maybe krypton or barium or xenon. They would find elements that are about half the size of uranium. Now, where did they come from? Could it be that uranium split into two pieces? I mean, that's unheard of. What could that be? Well, they didn't know. But Lisa had to get out of Germany. So how to get out? She was now, in a sense, trapped. She turned to the Great Dane, Niels Bohr. You're familiar with Niels Bohr. You're familiar with the Bohr atom, right? For which he gets the Nobel Prize. He was a person who helped many, many scientists, helped many Jewish people escape Germany. He helped her get out of Germany. coming over to Denmark, but he sent her to Sweden, outside of Stockholm, where he found a small job for her to do. She was now working up in Sweden, and she came up with an explanation of what was happening. She was visited by her nephew, Otto Frisch, also Austrian, also Jewish, also a physicist. And the two of them went cross-country skiing together. Well, he did. She didn't have skis, so she walked while he skied. And they were talking about what would happen if a slow neutron hit a uranium atom. And she said, I wonder if Niels Bohr is right about the fact that a nucleus could behave like a water droplet or a liquid drop. Could it oscillate and then break into two parts if a neutron were to hit it? She said, if that's the case, some energy would be released and we could calculate that energy. They sat down on a log, got up scratch paper, penciled it out, and she said, if that were to happen, I think about 200 million electron volts would be released. Now, 200 million electron volts is really not much energy, but for a nucleus, for one nucleus, that's a lot. In fact, it's about 1 or 10 million times more energy than a common chemical reaction. So, her eyes were opened. Wow, if this is the case, we have in a nuclear reaction 1 million times the amount of energy released compared to chemical reactions. Otto Frisch, her nephew, was an experimentalist. He had been working with Niels Bohr at Niels Bohr lab in Copenhagen. He went back to Copenhagen, and that very night, he put together an experiment. He bombarded uranium with neutrons, and he measured the energy, first person to try to measure the energy, and he got 200 million electron volts released per nuclear event. Exactly what they had predicted. Wow. As a side note, Arohan received the Nobel Prize for his work. In his acceptance speech, he never once mentioned the name of Lisa Meitner. Well, what is it that happens? Let's say that this is a uranium nucleus, and the red are protons, the white are neutrons. So let's suppose a slow neutron comes in and hits it. It gets absorbed, it causes it to split, and it splits into two roughly equal parts. We call them the fission products. And we now call them waste products also. They are radioactive, and those are the things we have to be careful of for a couple hundred years or so. So in addition to the fission products, there will also be some excess neutrons released. So this is the basics of what a nuclear fission event occurs. A neutron comes in, we end up with some fission fragments, we end up with some excess neutrons, and a lot of energy released, 200 million electron volts. Leo Szilard is a Hungarian Jew. There are 4 Hungarian Jews who were very involved with the whole Manhattan Project. I'll only talk about 2 of them tonight. One who I will not talk about won a Nobel Prize. It's amazing, from a small country like that, 4 Hungarian Jews, all of the same age, very involved in this. Leo Szilard lived out of a suitcase in hotels. He never had a house. He was in London. Well, he had to leave Europe because he was Jewish. He was standing at the corner for a red light, waiting for it to turn green, and it dawned on him, if that occurs, we could get a chain reaction to occur. How would that be? Let's go back to this. Here comes a neutron. it causes this to explode, separate, with 200 million electron volts released. What if this neutron hits another uranium, causing it to split, getting another 200 released? And what if a neutron from it causes another one to split, etc., etc.? We could have 200 million electron volts released, another 200, another 200, another 200. We could have a constant release of energy, and that's a chain reaction. And that's what you want to occur in a nuclear reactor, where you have a constant release of energy that we could use. But what if this neutron causes split, and suppose this one also causes one to split? Then we would have 200 released here, but this one would cause 200 more, and this one up here would cause 200 more, so we would have 400 released here. What if each of those produced two neutrons? We could have 800, 1600, and we have a mushroom effect, exponential growth, and that's a bomb. So, depending on if you have one or more than one, you get a chain reaction of either type, constant or something that goes explosive. Leo Szilard had this idea. He patented it and gave it to the Royal Navy of Britain so that he would get credit, but yet the Germans wouldn't know about it. Leo Szilard then came over to the United States. He was very much anti-Hitler, and he was very concerned that the Germans were going to be ahead of them and make an atomic bomb. He wrote a letter to President Roosevelt, but he knew that he couldn't sign a letter. Why would Roosevelt read a letter by this unknown? So he went to Einstein and said, "Einstein, would you sign this?" Einstein made a few comments. Szilard went back to New Jersey. Einstein was in Long Island for the summer. Szilard retyped it, came back to Einstein. Einstein signed it, and now they wanted to send it to President Roosevelt. Szilard was scared. He knew that the Germans knew everything there is to know about nuclear physics. Where was the first experiments done that really explained it? Arohan's lab in Berlin. He knew that they had captured heavy water plant in Norway when they captured the country of Norway and were shipping heavy water into Germany. I won't go into it, but heavy water has a use in the development of atomic energy. He also knew that they were shipping uranium from the Belgian Congo into Germany. He was scared that the Germans may be making a bomb. And if they had the bomb before we did, they would ruin London, they would ruin England, and they would take over the world. But now that they got their letter signed by Einstein, what do you do with it? They had a man by the name of Alexander Sachs, who was an economist, who knew some science, and they got him to take it to FDR. And the reason is he was a personal friend of FDR. He had an appointment for early September of '39. However, on September 1st, Hitler invaded Poland. And all of a sudden, FDR was very involved with thinking about other things other than having a friend come in to visit him. So a couple of weeks delay, and Alexander Sachs finally gets into FDR and explains to him what's going on and says there's three possible things that can happen with this newly discovered scientific discovery. One, it could be that nuclear reactor could be made to generate electricity. Two, the nuclear field could be used in the field of medicine for both diagnostic and for curing purposes. And three, it's possible that a weapon of extreme power could be made. FDR decided that something should be pursued, and he put a man by the name of Briggs in charge of it. Briggs, however, had about no interest in pursuing it at all. The scientists, however, were not sitting around doing nothing. They were doing things, especially Fermi and Szilard in New York City at Columbia University. Fermi continued to bombard uranium there. And what he wanted to know, though, is which of the isotopes of uranium underwent fission. Uranium has two major isotopes, uranium-238 and uranium-235. The difference being that uranium-238 has 3 more neutrons than uranium-235. The question is, which of these isotopes underwent fission? Both? Just one? Which one? The only way to know would be to separate the isotopes and bombard each one separately to learn the answer. So he sent a sample of uranium to AOC Neer at the University of Minnesota, world's leading expert in mass spectrometry, who built a special glass mass spectrometer to do this. Now, he would send ionized uranium ions down the glass tube at a fast speed through a magnetic field. So the glass tube was curved like this, and there's a magnetic field here. And if a charged ion passes through a magnetic field, there's a force exerted on it that causes it to curve. Uranium-238 has a higher mass than uranium-235, therefore more inertia, and so it's harder to make it curve than it is to get uranium-235 to curve. So they will be separated, and uranium-235 will take a sharper turn than uranium-238. So if you run this long enough, you get a separation. As long as you collect each, you can have them separated. Atom by atom, slow process. He did this. He put the results in an envelope, U.S. mail back to Fermi at Columbia. Fermi then bombarded them with uranium, with slow neutrons, and discovered that it's uranium-235 that undergoes fission, not uranium-238. That's bad news. Why? Uranium-238 is far more, there's much more uranium-238 than there is uranium-235. In a sample of uranium, over 99% is the wrong kind, uranium-238. Less than 1% is the uranium-235, which undergoes fission. If we're to do anything with this, make a nuclear reactor, make a bomb, whatever we wanted to do, we would have to separate the uranium-235 out of uranium, and boy, that's going to be tough. You can't do it by chemistry. We have wonderful chemical companies, but you can't do it by chemistry because it's all uranium. It behaves exactly alike chemically. The only thing you can do is a physical process, either the magnetic field or there's another method called gaseous diffusion. The Brits were certainly not doing nothing. They were being bombed every day. Their men were over in Europe getting killed and slaughtered. They wanted to find out if uranium is possible, if it's possible to make a bomb, and they were doing experiments to see about the feasibility. And their end result, their conclusion is, yes, it's possible to make a bomb. They sent their results over to Briggs in the United States. Oliphant. Okay, he's not British, he's Australian. But he was chairman of the physics department at the University of Manchester. He was wondering why the Americans aren't doing anything. He got onto a bomber plane, unheated, flew over to the United States, went to Washington, D.C., went to visit Briggs. Briggs, what are you doing with that mod report that we've sent you? Oh, you mean, as he opens a safe, you mean this report I put in the safe when I received it? Oliphant blew a gasket. What? You haven't even done anything. We're being killed over there, and you guys aren't doing a thing. He not only blew a gasket, he traveled across the nation. He went to Columbia to talk to Fermi. He went to California to talk to the scientists out there. You got to do something. Get going. At the end of the war, Leo Szilard said, America owes a big debt of gratitude for this man to kicking America in the rear end. Shortly after, we entered the war against both Germany and Japan. Groves, Leslie Groves. I was an Army brat. My dad was a chaplain in the Army. I wanted to be in the Army. I wanted to go to West Point. They wouldn't accept me. I went to the University of Washington for a year or two, then to MIT for 2 years, finally into West Point. Graduated in 4 years, fourth in the class. I've spent a couple decades already in the Army. My last job was being in charge of all military construction in the United States for the Army. I was spending $600 million each month. I had just finished building the largest building in the world, the Pentagon. And I was ready for an overseas assignment where the war was. Get me out of this country and into the war. I was at a committee hearing in the House of Representatives, and I walked out at the end of it, and I met my boss in the hallway, and he said, "Colonel Groves, we got a job assignment for you." "Yes, sir, I'm ready to go overseas." "Well, that's not what we're thinking of. We have something called the Manhattan Project we'd like for you to work on." "No way do I want to work on that." I said, "I've heard about it. It isn't going anywhere. That thing is impossible to do. By gosh sakes, I mean, their entire annual budget I've been spending in 1 week. They don't have any money, and it's an impossible project. I don't want to have anything to do with it." "I'm sorry, you've already been appointed. There's no change about it." "Yes, sir." But wait, these guys are eggheads. I mean, they're Nobel Prize winners. I'm going to have to work. They're going to take directions from me? I mean, they won't listen to me. I'm just a colonel. "We're aware of that. Your orders for general come through in 3 days." "Yes, sir." I talked with the people who have already been working on the project just a little bit. They had looked at some property in Oak Ridge, Tennessee for possible purchase. 3 days after being appointed, I traveled to Oak Ridge, about 50,000 acres. We don't fool around. I went up to Columbia to visit Fermi and a man by the name of Dunning. Dunning was working on something called gaseous diffusion. Very, very difficult thing. He was almost hopeless, but I liked Dunning, and I certainly liked Fermi. Before I go any further, let me tell you something about me, but I will let you read it. I don't want to read that stuff. But don't forget, it's the conclusion that's important. In a war, you drive hard. I then traveled out to California to meet Ernest Lawrence. Ernest Lawrence was a Nobel Prize winner, American bred and born in South Dakota. He had invented the cyclotron. Now, this is a cyclotron, and this is the main part right here. Then what is this thing, and what is that thing? These are coils of wire to form a magnet, and this iron, and so that there's a large magnetic field in this cyclotron area here. And the cyclotron is a particle accelerator. It gets particles going very, very fast. When you get them going very, very fast, you can slam them into another particle and see what happens to get nuclear reactions to occur. He had developed many cyclotrons, for which he gets the Nobel Prize. And that is one of the bigger ones. I liked Lawrence. I was considering putting him in charge of all the scientists because he knew what should be going on. But I was scared to take him away because I could tell already that the whole magnetic fields and the cyclotron idea was something so crucial to what we were doing that I couldn't take him away from that. Well, he introduced me to a colleague, Oppenheimer, who was there at Berkeley also. I met Oppie. We're totally different. He was skinny. I was hefty. He was weak. I was robust. He was an intellectual. I was practical. He knew 6 or 7 languages. I kind of knew English, but I liked him. But Colonel Nichols, that guy who, remember the conclusion? He wanted to work for me? Don't forget the conclusion. That's more important than the other stuff he said. Colonel Nichols was my security advisor. He did not like Oppenheimer. Why not? His wife, Kitty, card-carrying communist. His brother, Frank, professor of physics, University of Minnesota, card-carrying communist. Well, what about Oppenheimer? Is he? No, but he belongs to every left-leaning organization on the West Coast. You can't have him, General. But I liked him. He could understand the big picture. He had the capacity to explain something in science so concisely that you understood it almost immediately. In one sentence or two, he could explain something complex, you thought you understood it. These other guys, they could take 2, 3, 4 paragraphs to explain it, and when they're done, your head is swimming. You don't know what they said. This guy was clear, concise. He knew what he was doing. He understood the big picture. I liked him. It took many months, but we finally got security clearance for Robert Oppenheimer. Now I want to emphasize that there was certainly guidance from civilians even above me. And here is a group of some, all at one meeting, who are giving guidance to the entire project. Over on the left, there's Ernest Lawrence. You've already met him. Here's Arthur Compton, Nobel Prize winner. By the way, Ernest is a Nobel Prize winner. Arthur Compton, Nobel Prize winning physics, University of Chicago. Vannevar Bush, past vice president of MIT, now head of the Office of National Research and Development, one of the leaders in science development in the national government in America. James Conant, best organic chemist in America, also president of Harvard. Carl Compton, oh, same name as over here. Yes, brother, president of MIT. And Alfred Loomis, physicist who owned his own private research lab in which he did research, also an industrialist and a businessman. These were just some of the people who gave overall guidance. There were others too. But in one picture we have an assembly of them. Let's go back to Compton at the University of Chicago. He invited Fermi to come to Chicago in order to build a nuclear reactor. So Fermi came and they built the world's first nuclear reactor. It's called a nuclear pile rather than a reactor because it was a pile of carbon. Why carbon? Carbon would slow down neutrons. We discovered that the kind of neutron that causes uranium-235 to fission is a slow neutron. A fast neutron just kind of bounces off. A slow neutron will cause it to split. So we had to get slow neutrons. So you bombard it with slow neutrons, and the way to do that is to have it hit something small. How do you slow down something? Let's say a pool ball. You have a pool ball. How would you slow it down? If you hit a BB, would that slow it down? What if you hit the barrier of the pool table? That doesn't slow it down much either, does it? But what if you hit another billiard ball? Right? So how do you get a neutron to slow down? Have it hit something about the same size. You don't want to hit hydrogen because hydrogen will absorb it and you won't have the neutron. It'll become deuterium, proton and neutron. But you want it to hit something smaller. Carbon was one thing that was available that, okay, it's 12 times bigger. But nevertheless, after a few collisions with carbon, you'd have a slow neutron. So they took carbon and sawed the carbon, put it into here. It could be black as the ace of spades every night from sawing it, and put uranium slugs in the inside, and then put cadmium rods in here. And you can see a man here pulling the cadmium rod out. Why the cadmium rods? Cadmium absorbs neutrons, just sucks them up. So if the cadmium rod is in here, the reaction will not occur. So Fermi, by the way, there are no cameras were ever allowed. There are no pictures, so this is an artist's sketch. So Fermi up here would tell this man, okay, pull the cadmium rod out another 6 inches. They would watch the needle go up. Fermi would do his slide rule. Okay, pull out another 6 months, 6 inches, goes up, does the slide rule work, etc. Finally, it got to the point where it's sustaining a reaction. He let it go for 2 minutes and said, shut it down, it's been successful. First man-made nuclear reaction occurred. 1 year almost after Pearl Harbor. Compton called Conant, the president of Harvard, on the telephone. The Italian navigator has just landed. Well, that's good. And how were the natives? The natives were friendly, meaning everything worked out right. We now knew. We weren't sitting around doing nothing while they were trying to do that. We were assuming that it worked, and I was spending money like mad. One at Oak Ridge, Tennessee, building something called Alpha 1, this large monstrosity to separate the isotopes of uranium so we can get uranium-235. We didn't know how much uranium-235 was needed for the bomb, but we knew that we needed a percentage of about 90 to 95% of the uranium that we put in the bomb had to be the uranium-235. That means a lot of effort to separate the isotopes. This is an example of using magnetic fields, like a bunch of cyclotrons or mass spectrometers, in order to separate the isotopes of uranium, called Alpha 1. Now, again, we needed magnetic fields, and how do you get magnetic fields? You have coils of wire passing electricity through them. What's wire usually made of? Copper. There was no copper available. Why not? You're in a war. It's being used for the brass of bullets and artillery shells. There's none available, even though we had the highest rating for purchasing. But silver is a conductor. I went to the Undersecretary of the Treasury and I said, we need some silver. How many ounces would you like? We need 5,000 to 10,000 tons. We got it from West Point. It was shipped to New Jersey. It was refined at Virginia. We shipped it to Milwaukee, to Alice Chalmers. They made it into wire. They shipped it to Oak Ridge. We put it into here and ran it for a month or two, and there's something wrong with it. The wire wasn't right. We shipped it right back to Milwaukee and said, do it again. Do you remember what that guy said about I was a driver? You're darn right I was a driver. Our men were being killed in the war. We want to get this thing done, and we don't accept sloppy work. We had a couple of these alphas. There were also some betas. We would take the product from the alpha, put it into beta, and do some more to enrich the uranium. These poor ladies had no idea what they're doing. Watch the needle. If it goes to the right, you turn this knob that way. If it goes to the left, you turn the knob the other way. Just keep that needle right at the top. They were regulating each one of those little magnets. No idea what they were doing. And that's the kind of secrecy that was throughout the Manhattan Project. But in a war, you get in a horse and you ride in 3 different directions at the same time. Alpha 1 was one direction. Gaseous diffusion is the second. About 5-10 miles away from Alpha 1, we built the gaseous diffusion plant. Dunning's idea of separating the isotopes by diffusing them through a filter and hoping that the uranium-235 makes it through better than the uranium-238. I was building this building before I knew what was going into it, because Dunning was having a very, very difficult time perfecting the gaseous diffusion. This building's 5 stories tall. It's a half a mile long. It's the biggest building in the world. I've now built the 2 biggest buildings in the world. Gaseous diffusion was finally put in there. It worked. Both the Alpha 1 and the gaseous diffusion worked, but they were very, very slow. Glenn Seaborg in California discovered plutonium-239. Now, how is that? If you bombard uranium-238, and we have plenty of that, that's more than 99% of uranium is that one, with a neutron, it can absorb the neutron and it just becomes bigger. It's still uranium, but it's now 239. But uranium-239 beta decays, that is, it spits out an electron. So uranium-239 spits out an electron. Well, if it loses an electron, that's the same as gaining a positive charge, isn't it? So now instead of 92 protons, there's 93 protons, and we give it another name, neptunium, which also is radioactive, spitting out an electron. And if it does, that's the same as gaining a positive charge. So there's now 94 protons, and that happens to be plutonium. And it's still 239 because that's the total number of neutrons and protons. So he had just been discovering this. And we realized theoretically that plutonium-239 and uranium-235 have very similar properties. And if one undergoes fission, the other one should be able to too. We would have to test it to see. By the way, uranium, neptunium, plutonium, ever hear of Uranus, Neptune, and Pluto? That's what they're named after. What do we do with this idea of plutonium? We're going to go to Hanford, Washington. And I bought 40,000 acres up in the desert of south central Washington near the Columbia River. I brought in workers to build nuclear reactors so that we could manufacture plutonium. We would go up to people, let's say, you're a carpenter, yes? Here, sign here. Why? Where will I be going? Can't tell you. When will I get back? Can't tell you. What will I be doing? Can't tell you. Sign here. These are the men just to build the place. And this is one of the 3 nuclear reactors we built at Hanford, Washington. But if we're going to create plutonium, that reactor now is going to have uranium in it and plutonium. How do we get the plutonium out? Well, let's say we take the fuel rods out. What do? You can chemically separate plutonium from uranium. They're different chemically, right? They have different numbers of protons and electrons. That's a chemical. But we have chemical industries. DuPont is the best. I went to DuPont. I talked to the president. I would like you guys to go to Hanford, Washington and build 3 nuclear reactors. If we're successful, it could win the war. He said, what's a reactor? I explained. He said, I can't make this decision myself. I have to ask my board of directors. Bring him in. He brought him in, 31. 31 hard-headed businessmen sitting around a table. And the president said that General Groves is here saying that he wants us to build something in Hanford, Washington. If successful, it could end the war. But I'm telling you, if it's not successful, it'll probably be the end of DuPont. What do you want to do? Will it end the war? It's hard to know. But the Germans probably are working on it. And if they get it before we do, it's over for us. No more questions were asked. The vote was unanimous. Go for it. With one stipulation, that they be paid cost plus $1. They would not make money on the war effort. That was the kind of patriotism we had in World War II. That was the 250 megawatts, million watts of power for each reactor. Fermi's first reactor has 1 watt. This is 250 million. This is what the inside of the one looks like. I interviewed over 250,000 people. Well, I didn't. We interviewed over 250,000 possible workers to run this, to get an average workload of 22-some thousand people. But once we created the plutonium in the nuclear reactors, we had to extract it chemically. So I built 2 other plants, here is one, just to separate plutonium from uranium. 3 football fields long, these buildings are. We will put the uranium rods with plutonium in at one end, and they would work their way through the building, having acid baths, different things happening to them all the way through without ever a person touching that stuff. It was too radioactive hot. It had to all be done by automatic instruments. And this was successful. Well, we had to have something for the eggheads to do too. Remember Los Alamos? Oppenheimer said, hey, I was at Los Alamos, New Mexico. That's a good place to bring the eggheads. It's out in the middle of nowhere. We can have absolute privacy there. I went there 2 months after I was put in charge of the Manhattan Project. I bought 50,000 acres at Los Alamos. Where's Los Alamos? Here's a map of New Mexico. Here's Albuquerque, the largest city. Here's Santa Fe, the capital. And Los Alamos is up here in the mountains in northern New Mexico. There was nothing there. I had to build everything. I had to build housing, labs, you name it. And there we brought the eggheads, including Oppenheimer and his crew. We gathered the biggest collection of eggheads in one place the world has ever seen. How did I get them? I went to the universities. I'm at the University of Wisconsin. I say, we need you. Why? I can't tell you. Where am I going? Can't tell you. But you can bring your wife and your kids. I got them. I got 50% of the people I interviewed. Other people at the University of Wisconsin were wondering where some of their friends were disappearing. They went to the library and found out that books on New Mexico had been checked out by some of them. They were kind of wondering why. We had to educate each other. Most of us, although smart, knew very little about the whole nuclear physics part. And we had people doing other things other than nuclear physics. We had Nobel Prize winners and Nobel Prize winners to be all over the place. Here's a few of them. Hans Bethe, Nobel Prize winner at Cornell. Actually, he's German. He's Jewish. Christian by faith, but Jewish by blood. But because of the Jewish by blood, he had to leave Germany. Came to Cornell, Nobel Prize winner. I put him in charge of the theoretical work. Good man. Edward Teller, he became known as the father of the hydrogen bomb. He was there. He's another one of these Hungarian Jews I mentioned before. He was a thorn in my side. He wanted to develop the hydrogen bomb. We called it the super bomb at that time. Oppie, let's build the super bomb. It's 1,000 times more powerful than the atomic bomb. Why build a little atomic bomb when we can build a super bomb? It's big, we can do it. Edward, would you be quiet? We haven't learned how to build a regular atomic bomb yet, let alone build something bigger than that. But we can do it, we gotta do it. Oh, he was a thorn in my side. He was a pain in the neck. And it got worse as the years went by. Eisenhower invaded Normandy, and the Americans were marching into Germany. And in April of that year, FDR passed away, just weeks before Hitler was defeated. But when he passed away, I had to call the men together and give a pep talk. We've lost a great man, a leader for us, but we have to carry on. The war is still going on, although it's not going on now in Germany, at least in a couple of weeks, so we knew that the German war was going to be ending soon. It is still raging in Japan. Well, we built Trinity Site down in the middle of New Mexico in order to test the atomic bomb. Now, where is the Trinity Site? Again, here is Los Alamos. We drove down this road to Socorro and then over to Alamogordo area where the Trinity Site was. And at the Trinity Site, we built a tower, and we're going to test one of the plutonium bombs at the top of the tower. Why at the top of the tower? Because when we dropped the bomb, it would be exploded in the air, not on the ground, because in the air, it would have more of an explosive impact. So we wanted it to be above air somewhat. This is the plutonium bomb right here, getting ready to be raised up to the top. Now, let me explain something about critical mass. Let's suppose you have a sample of uranium-235 or plutonium-239, and a neutron is released on the inside. Two things could happen to that neutron. One is it could escape. If it escapes, it will not cause a nuclear reaction, right? The other possibility is it could be absorbed and cause a nuclear reaction. Now, if it's a very, very small sample, it's a good chance it will escape, right? If it's a big, big, big sample, there's a good chance it will be captured and another nuclear reaction will occur. So where is the cutoff? The cutoff is what we call the critical mass, the smallest amount of mass that you need in order for a nuclear reaction to continue on a continuous basis. That's what's called the critical mass. You need that for a reactor to be working. For plutonium and for uranium, they are different in critical masses. But it's also because the devices are different. Plutonium was a little bit more sensitive than uranium. And so the devices had to be done differently. Plutonium, we were manufacturing at Hanford in bigger quantities than we were getting uranium-235 at Oak Ridge, Tennessee. But it was difficult to get the plutonium to work. It being more sensitive, if we put it together, if we had, let's say, half of a critical mass here and another half here, bring them together so that you have a critical mass that explodes, let's say. Somewhere, if you bring them together too slowly, it will start exploding before they're all together. And it fizzles out. So you got to get them together real fast. And for plutonium, we had no way of getting them together real fast other than having kind of a sphere, putting explosive charges around on the outside, blasting them simultaneously to draw these together very quickly. It was very, very difficult experimentally to get that designed. We did it, we thought, but it was too risky to try to drop one on Japan without testing it. So we had to test this method for plutonium. And we tested it on July 16th of 45. Boy, we were supposed to test it in the early of the morning, and it poured and it rained. Oh my gosh, but it worked. That man Fermi, he's a physicist. There's two kinds, experimentalist and a theorist, and he was both. He was number one in both areas. You know what he did? He took some paper, he tore it into little pieces. When the shock wave came by, he tossed them up in the air, and then afterwards he paced out how far each of them went. Then he did a little calculation and said, I think it was about 10,000 TNT equivalent worth of energy that was released. And a few days later, when we did the actual calculation, he was right about on target. We still don't know how he figured that one out. That guy's amazing. Groves was there also, of course, as well as some other people who needed to see it. It was successful. We're now ready. But what did we do with the information? First thing I had to do was tell Truman. Truman was now president. When he became president, he did not know a single thing about the Manhattan Project about nuclear energy. It wasn't until about a week later that he was told. He was for it, although he didn't understand too much about it. But the more he knew, the more he wanted to know. He was in Potsdam, Germany, right outside of Berlin on the southern edge, with Churchill and Stalin, to plan about the separation of Germany and everything. It's a week to 10-day conference. He wanted to know, were we successful or not? I wired him, we were successful. He told Churchill. Churchill was elated, because that meant that we could maybe end the war against Japan. Stalin knew already. Security had been breached. Leo Szilard, the Hungarian Jew, who came up with the idea of a chain reaction, who pushed for the development of the Germans are going to kill it, the Germans are going to develop and they're going to wipe us all out. He now says, oh, wait a minute, we shouldn't use the bomb. People might get hurt. People might get killed. What do you mean? We've developed a bomb in order to possibly use it. What do you mean, don't use it? Well, I mean, the Germans are already defeated. Yeah, but we're fighting the Japanese too. Just because you're from Europe doesn't mean that's the end of the world over there. These eggheads, I can't tell you, they can drive you crazy. You're familiar with the Iwo Jima, mostly because of this flag. Let me tell you a little bit about Iwo Jima. Here's Japan. Here's Iwo Jima on a map. And here's Tinian Island, which we had B-29s. We were trying to bomb Japan from Tinian Island with B-29s. Unfortunately, we had to go over Iwo Jima, and they had 2 air bases there. And they were shooting our planes down or harassing them to the point where it was a real problem to bomb Japan. We had to take out Iwo Jima. We sent in 60,000 U.S. Marines. But before they entered, we bombarded that island day after day with heavy shells from our battleships and cruisers. We blew it to smithereens. Then we sent 60,000 Marines in to invade Iwo Jima. Over 6,000 lost their lives. Over 10% death rate, the highest death rate the U.S. Marines have ever faced in a battle. 1/3 American casualties. But I want to look at the other side. The Japanese, 21,000 were defending it against our 60,000. Of the 21,000 Japanese defending it, 20,000 lost their lives. Only 1,000 surrendered or were captured. Let's put this into percentages. That's 95% were killed and only 5% surrendered or were captured. That's the Japanese mentality throughout the entire Pacific War. The word surrender is not part of their vocabulary. They would not surrender. And that's true in Iwo Jima as well as all the other islands that we're fighting. General LeMay was in charge of bombing Japan. When he learned about the death rate of the Marines at Iwo Jima, he was appalled, and he decided he is going to blast Japan as heavily as he can. He now flew B-29s from Iwo Jima airports. In one night, March 9th, he sent over 300 new B-29 bombers to Tokyo, and they dropped enough bombs to kill 100,000 Japanese in one night, injuring 1 million and making 1.5 million homeless. Did the Japanese surrender? No. He continued bombing Japan. He bombed about 70 different cities, killing hundreds of thousands of more Japanese. The Japanese would not surrender. Here's some of the status of what was happening. By now, the Japanese were using kamikaze pilots that you're familiar with. They would dive their plane right into a ship, sacrificing themselves, hoping to sink a ship, which they were successful. We were losing 5,000 Americans each week in the Pacific. If you're president, if you did not use the bomb, how would you tell the mother of one of these boys that you could have ended the war, but you didn't and your son died? MacArthur estimated we have 300,000 American casualties if we invaded Japan. And here's an interesting one. There were 100,000 Americans who were held captive prisoners of war in Japan, and Japan let it be known that they would be beheaded if we ever invaded Japan. Here's the plans. Here's Japan. Here's the island of Kyushu. We would send in an invasion force at Kyushu in November, try to set up air bases from which we could bomb. Then in March of 46, we would send in an invasion force into the island Honshu up here. What are some of the figures? At the first island, Kyushu, down below, November 1st, 5 times as many American soldiers coming in as what we sent into Normandy. That was the plan. Half a year later, 1 million American troops coming in at Honshu Island. LeMay would be dropping 100,000 tons of bombs each month. General Marshall, if you're familiar with, he had the Marshall Plan that rebuilt Europe, rebuilt Germany. Okay. He said the following: we regarded the matter of dropping the atomic bomb as exceedingly important. We had just gone through a bitter experience at Okinawa, which I didn't even tell you about, when the Americans lost more than 12,500 killed and missing, and the Japanese more than 100,000 killed in 82 days of fighting. The Japanese had demonstrated in many cases they would not surrender and they would fight to the death. It was expected that resistance in Japan would be even more severe. We had had the 100,000 people killed in Tokyo on one night of conventional bombs. That's what I told you about March 9th. And it had seemingly no effect whatsoever. It destroyed the Japanese cities, yes, but their morale was not affected as far as we could tell, not at all. So it seemed quite necessary, if we could, to shock them into action. We had to end the war. We had to save American lives. There's an interim committee headed by the Secretary of War, Stinson. Now, Secretary of War is what we now call Secretary of Defense. And here's a bunch of civilians that were part of this interim committee. and you recognize some of these names. They're all civilians. And then there's a science panel, and you will recognize these names. They would give advice. This whole thing was guided by civilians. And they came up with a recommendation from the interim committee, 3 points. Use the bomb on a military target, no warning. There was considerable discussion about a warning. Their decision was no warning. Glenn Seaborg, who discovered plutonium, simply said, it's hard for anyone who didn't live through World War II to imagine the desperation and sense of impending doom that we felt. We sent a radio message to the Japanese from San Francisco, saying the following: we call upon the government of Japan to proclaim now the unconditional surrender of all Japanese armed forces. The alternative is utter destruction. We're now ready with the uranium bomb, Little Boy. The bomb, Little Boy, put together from uranium at Oak Ridge, Tennessee, was shipped to Tinian Island on the USS Indianapolis. After it delivered Little Boy at Tinian Island, the USS Indianapolis went on towards the Philippines. Before it got there, a Japanese torpedo sunk it, taking almost all lives of over 1,000 men. But they had delivered Little Boy to Tinian Island. Now, Little Boy is uranium, and let's explain how it would work. There would be something, uranium up here and uranium down here. Each of them is less than the critical mass. They're separated. There's an explosive up here. So just like a gun, and it's called the gun method, blam, and you shoot this bullet down here. Now we have a critical mass, bigger than a critical mass, and for the uranium, that's about 140 pounds, and you get the explosion. It's a simple device. We could not use that for plutonium because we could not get this to go fast enough. We'd have needed a gun that would be 20 or 30 feet long in order to do it by the gun method for plutonium. That's why plutonium had to be done very, very differently. We loaded it into Enola Gay, a new B-29, piloted by Colonel Tibbets, named after his mother, Enola Gay. I put Colonel Tibbets in charge of the people from the Air Corps, 2,500 of them, to plan on how to deliver the bomb, how to develop the airplanes. They cleared out almost everything in the airplane that wasn't needed. Increased the size of the bomb bay doors because these bombs were much, much bigger than conventional bombs. They had to practice dropping heavy bombs and getting out of there so that they were gone before the explosion occurred. We didn't know what kind of shock wave or anything like that would occur. So they practiced at Winford Air Base in Utah for about a half a year. Enola Gay took off from Tinian Island and dropped the first bomb on Hiroshima, August 6th. Did the Japanese surrender? No, they didn't. Their radios said a small number of B-29s penetrated into Hiroshima and dropped a small number of bombs, and as a result, a considerable number of homes were reduced to ashes. We now did drop leaflets all over Japan, millions of them. We are in possession of the most destructive explosive ever developed by man. We explained the whole thing. I won't read it all. Basically said, surrender now or we will continue. Now, for uranium, we would not be having enough uranium for another, perhaps a few months. It was so slow to get uranium. But plutonium was a different matter. we could probably get a bomb every maybe week or 2 weeks with plutonium. So we had already used one at Trinity, and we are now getting ready to use one a few days after Hiroshima. The Fat Man. You recall there was a big sphere for the plutonium at Trinity Tower. And if we needed, we could get more plutonium weapons every week or 2. It was dropped in Nagasaki 3 days later. In each case, approximately 100,000 people. Maybe it's 80,000, maybe 100,000. Some people lingering deaths over the years. So let's just say 100,000 deaths. And each one total of about 200,000. Now the Japanese decided to surrender. The emperor told his generals, I know that you want to continue, because the generals wanted to continue. He said, but we're done. So they signed a peace agreement on the USS Missouri under General MacArthur's guidance. And so what happened? There was jubilation in America. The war is over. Our men were no longer killed. By the way, let me go back to that 100,000 American prisoners in Japan that they said were going to be beheaded. Would they? Let me make a comparison. In Germany, they had American prisoners of war. In the American prisoners of war for Germany, 99% came home. Only 1% did not make it home. In Japan, they had American prisoners of war. 37% never made it home. There's a big difference between 37% and 1%. There's a good chance that they were serious when they said that they would kill and behead the 100,000 American prisoners if we entered. What happened to Oppie? He became the most popular man in America. Everyone wanted him to give a talk. He was in high demand. People who had never heard of him, all of a sudden, man, he's something. President Truman said, what has been done is the greatest achievement of organized science in history. Done under high pressure without failure. We've spent $2 billion on the greatest scientific gamble and won. Here's modern Hiroshima. And they kept this building as a reminder. We saw this in the previous slide. And what about Oppenheimer? What happened to him? He became Einstein's boss. Well, no, not really. No one told Einstein what to do. But administratively, he was put in charge of the Institute for Advanced Studies at Princeton for 2 decades. And that's where Einstein had been working. Einstein worked there until he died in 1955. Oppenheimer continued for another 11 years. However, Physics Today, a journal that all physicists get, had their very, very first issue ever, 1948. Notice there's no name on the front page. There's no picture of a person on the front page. But everyone knew what the article was about because of the hat. However, things were not so good for Oppie. Way back when, a friend of his who was a French professor at Berkeley approached Oppenheimer and said, I have a friend in Russia that I can get information to if you would like to. And Oppenheimer declined. He said, no, I'm not interested. But he didn't tell me. He should have told me, a violation of the protocol. And in addition, after the war, Edward Teller, the thorn in the side of Oppenheimer, kept saying, super bomb, we got to make the super bomb. And there was growing agreement that we should get the super bomb. But Oppenheimer said, no, we don't need it. And for those 2 reasons, the Atomic Energy Commission eventually stripped Oppenheimer of security clearance. The very man who developed the atomic bomb scientifically stripped of his clearance. However, 10 years later, in 1963, President Johnson made amends, gave him the Enrico Fermi Award, kind of like all is forgiven. Oppenheimer died in 1967. The names of Oppenheimer and Groves are linked together. They're forever linked together. You can't have one without the other. Some people love us, some people hate us. They hate us because we killed 200,000 civilians in 2 strokes with 2 atomic bombs. We now have to live with this mushroom cloud hanging over us of everyone has so many atomic bombs. Who knows if the US and USR will go at each other and collaborate each other. Mutual destruction. Will I, as an innocent citizen, be here today and gone tomorrow without my having a say about it? But there's others who say 200,000 lost their lives. But perhaps we saved 1 million Japanese civilians by not invading. Any war kills far more civilians than military people. If an invasion had occurred into Japan, many, many civilians would have lost their lives. In addition, perhaps the 100,000 American soldiers would have lost, the POWs would have lost their lives. In addition, maybe 100,000 American men invading Japan perhaps would have lost their lives. Maybe it saved lives. These are things that are hard to know. Let's look at it one more way. In World War II, maybe 70 million people lost their lives. No one knows for sure. And again, most are civilians. 200,000 lost their lives because of the atomic bomb. That's much less than 0.5% of all the deaths of World War II. That means, looking at it the other way, 99.5%, even more than that, of all deaths in World War II occurred by things other than the atomic bomb. And the atomic bomb put a stop to it. And no atomic bombs have been used since for the last 75 years.